Okay, so good morning, everybody. New week for the course of Introduction to Machine Learning and Evolutionary Robotics. So, let's start with the usual recap that today will be particularly short because in more or less 15 minutes we will host Dr. Faggionato for a seminar on an application of natural language processing on so-called low resources languages. So languages for natural languages spoken by humans, for which there are basically few documents that can be used for annotation and learning using machine learning techniques. Okay, so let's start with the recap. Last lecture we introduced this new big topic of the course, which is text mining, which is basically, from our point of view, the application of machine learning technique to the processing of natural language. Okay, so actually what we are doing is applying together the techniques that we saw in the first part of the course, machine learning techniques, in particular supervised learning techniques, and other methods which are usually thought to be part of the so-called natural language processing domain, okay, which is basically every tool that can be used for processing natural language. With natural, we mean that the language is spoken naturally by human beings. Okay, so we also say that you should have lower expectations in terms of the quality of the results when you apply machine learning techniques to natural language, because for its intrinsic nature, natural language is interpretable. Okay, so what could be an obvious interpretation for me as a human being, as an individual, could be wrong for you, who are different human beings and different individuals. We started, after this sort of definition, we started reasoning about examples of application of text mining. We reasoned about the problem of finding which is the, let's say, mood about a brand, in particular looking at the text which is being written in Twitter, so looking at the Twitter posts, also called tweets. And this is an example of sentiment analysis, because basically we want to understand what is the sentiment of the people who are writing about the brand we are interested in Twitter when they were writing what they wrote. Okay, so another example of problem is the case in which you want to understand which are the main topics in a collection of documents. We also use this example to introduce the term corpus. Okay, so corpus is a text mining jargon term for saying a collection of documents. In particular, this case could be, in this example, we assume to have some possibly thousands, hundreds of letters written by soldiers during the First World War, and we would like to understand which were the main topics of these letters. Not that this is a broad definition of the problem. It's pretty easy to understand which is the knowledge need, the knowledge hole that we are trying to fill. Okay, we want to know what the soldiers were talking about, but if you try to put it in an abstract form, in such a way that can be tackled using text mining techniques, you have to provide a more formal definition. So what is a topic, what is a letter, and so on. Which is the in case a topic is a broad definition that can tolerate many topics in a single letter. What is an important topic? So what is the importance of the topic, and so on. These were just examples for introducing let's say a broad categorization of possible problems in common tasks in natural language processing. Just a few names. Text categorization is basically the classification, the name for classification when you deal with text. Then we have clustering, okay, which is also the name of basically the main kind of unsupervised learning that we will see for part of you at the end of this course, and for the other part, this is a topic of the course by Professor Trevisani. Then we have entity extraction. So when you have some text you want to extract mention to some specific kind of entities, like, I don't know, names of cities, name of peoples, and so on. Sentiment analysis, we saw a specific example of this. So you want to take one short piece of text, for example, one tweet, and you want to understand what was the sentiment of the writer of the tweet. Let me check if we have okay, our guest is coming. Hi Christian, are you there?
Yes, I'm here.
Okay, perfect. Welcome. We
Thank
are
you.
already here. Basically, we are ready. I'm just doing the usual recap of the last lecture before starting. So if you can wait for another
No
couple
worries.
of minutes. Okay,
No
perfect.
worries.
Thank you. Okay, so we were saying which are most common tasks of text mining. We were arrived at sentiment analysis. Another common task is summarization, which is a task that we will not analyze in this course. Okay, that consists in making shorter a piece of text, a document, without possibly losing the information, the main information that is contained in the document. Another very interesting task that is gaining more and more popularity in the recent past is natural language generation. So, okay, that's probably not even considered part of NLP by someone, okay, because you have these different kind of thing that you are doing with natural language. In one case, you process it, you assume it exists, and you want to extract some information out of it. In the case of natural language generation, basically it's the opposite path. Okay, you have the information and you want to encode the information in a piece of natural language. Usually there is a twofold goal. One is that the information is inside the document. The second one is that the document appears like it has been written by a human, so it is written using natural language. This is a very popular game. It is gaining popularity in the recent past, and for this and for many other of the tasks here, the main tool is basically deep learning. Okay, and deep learning is also part of the techniques that our guest will reason about today. We also discussed quite a lot about this third task. This is an example of a task which is, let's say, not properly an instance of these common tasks, but however it's a task related to text mining. Okay, we have some textual information and we want to extract some knowledge. The knowledge that we want to extract in this case is the relevance of a citation. So we assume to have two scientific papers, scientific articles, A and B, and we assume that A is citing B somewhere in the document, for example here, okay, and we want to quantify the relevance of citation. Also in this case, note that we have a broad description of the problem that we want to solve, and the first step, which is basically possibly the hardest step in this case, is to formalize this problem in such a way that can be solved using machine learning techniques. Okay, so here in particular, the fact that the problem, the difficulty comes out from the fact that we don't exactly know what the relevance of a citation is. While we know what a topic, we all know more or less, maybe we are not able to define, but we know what a topic of discussion is. The relevance of a citation from a paper to another paper is probably something that is known only by a small community, which is the academic community. So just defining which is the problem here is difficult. Okay, we saw which is the general framework for tackling text mining problem, the general path. Okay, we want to, as usual, formalize the problem in such a way that we can precisely define what's an input and what's an output. That done, we know that we master, maybe master is too much, a subset of supervised techniques, learning techniques, which are able to process numbers and categorical values. Text is not a number, well, a document is not a number or a numerical vector, at least if you take it as it is, nor a set of categorical values, so we need a way to transform text in numbers or categorical variables. And we started seeing how to do this while reasoning about the task of sentiment analysis, which can be taken as a regression problem, like in this case, where the y is a number basically meaning the positivity of the sentiment, or a binary classification problem, positive, negative, or maybe a multi-class classification problem. Here we see an example of three categories which are basically ordinal instead of categorical. However, we also say that in other kinds of more complex forms of sentiment analysis, we can describe the sentiment along different lines, not just one being positive, negative, okay? Maybe degree of surprise, degree of angriness, degree or I don't know, other things. There are basically 7 big categories of sentiment, but I never remember them. The first problem is how to transform the text, and we just introduced, that was the last slide of previous lecture, we introduced the approach which is called bag of words, which simply consists in counting the occurrences of each word in each document by considering only the words in a dictionary. The usual approach is that the dictionary is considered to be composed of all the words appearing in the corpus, so in the union of all documents. Okay, that said, if there are no questions, and I assume if you have questions, please write them down and keep them warm for the end of the lecture. Now I think we can proceed with the seminar. So, Christian, the first thing that I have to do is to make you
yes.
a speaker. Let me see. Imposta come redattore. Ok. Ok. Perfect.
Okay.
Okay, now you should be able to share the screen. Did you receive the email saying that I'm going to record? Are you okay with that?
Yeah.
Okay, perfect.
Perfectly okay with that.
While you share the screen, before starting, well, I first introduce you. So, dear students, we today have Dr. Christian Faggionato. Christian is a research fellow at the School of Oriental and African Studies at the University of London. He specialized in linguistics of Tibetan and Himalayan languages, and in recent years he has been working with machine learning frameworks for natural language processing, creating and investigating corpora of various Central Asian languages. Okay, so today we will see a very peculiar way of applying text mining techniques to a problem which is not the usual problem that we deal with, which is basically related to business processes. Okay, so today we are reasoning with pure knowledge, which is a very nice thing. Okay, while you prepare, so I'm stopping my screen sharing. So okay, I'm seeing your screen. Just give me a moment because I need to capture the screen for the recording.
Okay, let me know if you see the screen now. It should be...
Yes, I see it. Okay, I see it.
Just so everyone should see it.
Before starting, just a moment, please.
Yep. You can hear me clearly. It's not... No.
Okay. Perfect. I see you. So I think you can start. Students, if you have any question, please write down in the chat I don't know, Christian, if you are able to see when someone is writing, there is a small red dot on the chat. But if you prefer, proceed, and then we can ask and discuss about all the things at the end of the presentation, if you
Okay,
prefer.
now that I'm sharing full screen, I don't see the chat.
Okay, don't worry, don't worry. I see it. If maybe if if I feel that the question is really important and urgent, I will stop you and make the question. Okay.
Okay, let's do it like that. Okay, so, well, thanks everybody for virtually attending this seminar, and thanks to Eric for inviting me. I'm very happy to introduce you the way that basically we apply neural network models in the processing and exploration of Tibetan text. As Eric said, I'm dealing with Tibetan Burman and Tibetan Himalayan language. I'm like a linguist, historical linguist, and during the past 3-4 years, I've been working at SOAS, the School of Oriental and African Studies in London, and our research project is mainly focused on verbs. So the primary objectives of this project is to annotate predicate argument structure of verbs in order to build like a corpus-based Tibetan verb lexicon. So basically a dictionary of verbs where each verbs will be an entry, and you will see like an example with all the possible argument structures of the verbs that appear in our corpus, but more on that later. So during the process of building the corpus, of tagging the corpus, or creating the data, we basically start to deal with a huge number like of text data, if you want to say. And so we start to approach the problem from an NLP perspective, so natural language processing perspective. And we tried different methods to address like the research problems that we wanted to address, of course. And we ended up using, at least for a couple of these tasks, some neural network models. As I said in the introduction of my seminar, I will show you how neural network models can be applied in the first part for the part of speech tagging and the verb argument detection of the chronic corpus of Tibetan text. The first part basically is like an introduction to Tibetan languages, and I will show you this fancy slide now with the Tibetan Burman languages. Afterwards, I will describe the full procedure that we use to develop a segmented part of speech tagged and chunk part corpus of Old Tibetan, which is an extremely low resource language. And in the second part of the seminar, I will show you the second task or research problem we try to address with a neural network model, which is like how a neural network model can be used to, in an efficient way, to solve a sequence labeling task. Basically to predict the correct labels for new sequences of words in classical Tibetan text. So the advantage of using neural models will be explained comparing them with other like statistical methods like memory-based tagger and rule-based method like CG3 constraint grammar. Again, more on that later. So here we have like a quick introduction to the family of Tibetan Burman languages. Tibetan, again, belongs to the Tibetan Burman languages. In green, you can see the area in Central Asia where Tibetan is spread. It goes as far west as Baltistan here, northern Pakistan, to like the eastern like regions in China here, and you have a huge variety of dialects. So nowadays we have modern Tibetan, we've spoken around Lhasa here in the central Tibetan like area, but you have like a huge variety of dialects, of course, and this is for modern Tibetan. You have like basically we are dealing with three corpora in our project. One is Old Tibetan, which is the oldest attested like documents written in Tibetan. They are from around the 8th century till the 10th century current era, so after Christ. And then you have like a huge amount of documents written in classical Tibetan, which is like the, let's say, the literate Tibetan. And you have like, of course, a huge amount of religious documents. Then you have like legal, historical documents till nowadays, like modern literature, let's say. It spanned like around like 1,000 years. It merged in the last century with modern Tibetan, which is the spoken form of the language. And then we have the third corpus, which is, of course, the modern spoken Tibetan. So we dealt with this like the chronic corpus made of 3 like sections. Now, a fast introduction on Tibetan. So what is Tibetan? Tibetan like is a fancy language, is a negative language, syllabic. Here you can see like a syllable of written like in classical Uchan script. Every syllable in the script is deriving from an Hindi Brahmi script. So it's kind of Devanagari used for Sanskrit and then from Hindi. So it belongs to that family of script. So there is nothing related to like ideograms like Chinese or anything. It's just like it's a script based like on syllables. So the core structure of the language, like is a syllable. You can see here a syllable with a root letter ga, with a vowel sound e on the top that modify the sound of the ga in ge. And then you have a bunch of other letters, can be like suffixes, secondary suffixes, like subscript letters. And all these suffixes and subscript and prefix, basically they modifying the sound of the consonant of the root letter. At the same time, since you have like so many homophones in Tibetan nowadays, because these are muted, they are used to distinguish the one word from the other. So this is like a word, is made of 2 syllables, like dam tun, and it means like exhibition. In terms of describing the language like is negative language. It means that the subject of transitive verbs is marked with a negative case. Is the structure, which is the most important feature of the language, subject, object, verb, with the verb, which is the main like element of the Tibetan language, is just at the end. Here, tsar, we have like the subject nga, then we have the object, which is like work, which is like this work, which is lam di, and then you have the verb. This is basically like a reduplicate like verb, but you have like subject, object, verb. And another like feature of the language is that it's a prodrop language. So many times subject is not there. And that can be an issue when we try to identify argument of verbs in terms of deciding if the argument has no markers, who is the subject, who is the object. So here we have like a classic like Tibetan sentence that this is like the meaning. I do not know whether I can complete this word. You pronounce this like nami she galte lamdi tar gammi tar. Okay, but that's irrelevant now for our task. Just want to know how it sounds. So now another thing about the punctuation, and that will be important when we will talk about word embeddings and creating like word embeddings for the training of our neural network model. So as you can see, there are no separation between words. So, and there are no even like separation between sentences. And this can be like a challenge. In fact, the only thing that can be like a sentence end sentence marker is this vertical line here, which is called she. But the weird thing is that sometimes it doesn't represent the end of the sentence. And then you have another punctuation symbol, which is this little dot at the right top of each syllable, which is like is called sec, and is a marker that mark the end of the syllable, but not the end of the word. So how you recognize word? Basically, you have all different kind of particles. They can be like final sentences particles. Then you have like case markers like Latin or other languages. So after a word, a noun, you have, I can show you here briefly, then we go back to what is this kind of weird like manuscript. There are like a case marker like this one here. So here you have a noun, and then you have a case marker after the noun. And the case marker indicate, this is a locative case marker now, indicate that this means in something. In this case, it means like inside the land of. Now we start to talk about the creation, of course, of the old Tibetan tree bank. So old Tibetan, as I said, is a very extremely low resource language. We have very little data to begin with. And not all the manuscript that we have available has been digitized properly. So we don't have bilingual data, for instance, and we have very little secondary resources available. This is a map showing the expansion of old Tibetan Empire in the 7th century. So it was occupying the main Central Asia, and at the time it was not even Buddhist. Like the Tibetan population and the Tibetan Empire was not related to any Buddhist religious movement or anything. So and again, it was really competing as a huge power within Central Asia. So at that time, of course, for probably legal needs, they introduced around the 7th century in Yarlung here, the south of you can see in the south here of Lhasa, they introduced the script. The script basically we call it now Old Tibetan, and most of them, this is an example of let me show you, of an Old Tibetan manuscript from the 7th to 11th century, and we basically recreate the Unicode code, transliterating this manuscript. Part of them have been OCR, and our task was to create a parsed corpus of Old Tibetan. But there are many challenges in addition to the low resource and under search ones that I just mentioned. So as I said, there are no sentence boundaries apart from the shed. But as I already said, basically the shed is not all the time an indicator of the end of a sentence. We can use the punctuation marker called sec, and we use then we will check also the what are called sentence final particles, to see if they were split in the tokenization process correctly. And we use again the sec, as I said, this little dot will be used for for the segmentation. Basically what we do, we recast this as a syllable tagging task following a method used by my colleague Maria Melin and Nathan Hill in 2017. And basically, we use tags for the beginning, the middle, and the end syllables. And then we recombine these syllables into words. Then we use like a dictionary lookup to check if the resulting words actually exist. And but the main problem with Old Tibetan is that there are no digital dictionary for Old Tibetan. In fact, there are no NLP tools for Old Tibetan at all. So what we decided to do, it was to convert Old Tibetan, first thing, to classical Tibetan. So normalize the Old Tibetan language to classical language in order to make use of the few existing NLP tools that we have for classical Tibetan. So the pipeline, it has been like the pre-processing, then the part of speech tagging, where the neural network model take action, then the chunk parsing, and then the post-processing. So briefly, like the pre-processing involves these three main tasks that we already said. The first one is the sentence segmentation that is based on shed, those vertical list symbols, and the final particles. Then we optimize the tokenization with the dictionary lookup, as I mentioned before. And then there is the normalization, which is based on this rule-based NLP tool, which is called CG3, which is a kind of Perl language, let's say, modified, that is able to create a rule in order to create like links between the part of speech tag. I will show you now how we we converted Old Tibetan to classical Tibetan. So this is an example of a peculiar like Old Tibetan feature. This is a gigu, reverse gigu, is a symbol for the vowel I, and in classical Tibetan is you can see that is reversed. Yeah, this is like Old Tibetan, no Tibetan. In this phase of the language, they coexist, reverse gigu and both normal gigu. But in classical Tibetan, you have only the left symbol. So I want to transform this shing in shing. How? There are like, this is another example, like a merged syllable. This is like a feature classic for like the Old Tibetan. This is like sheg step. You can see that two syllables here are merged together. Instead, like in classical Tibetan, you have the two syllable split together. And this is like a final sentence particles that I mentioned before that we use to define the sentence boundary. So basically, I created like a kind of set of rules from more specific to more general. This is an example of this rule that splits this syllable in two. And after we normalize with the CG3 methods, we tested different methods for part of speech tagging and to optimize the part of speech tagging. So first of all, we use like a memory based tagger. And what is a memory-based tagger? The memory-based tagger is based on kind of supervised learning. It's based on similarity-based reasoning. And basically the part of speech tag of a word in a particular context is extrapolated, we could say, from the most similar cases held in memory. And it's a kind of supervised learning approach that is useful when a tag corpus is available. A good thing about the tagging is just memories-based taggers it is not really time-consuming. It doesn't need so much pre-processing for the data. When we try to train the memory-based tagger and then the neural tagger, and more on that like in a bit. We use first just the classical training data, and then we added also the classical we added like the old Tibetan training data. So what we use like as a neural model, like a bit bidirectional like LSTM with the CRF, like conditional random field layer. And let's say that this tagger doesn't require pre-processing, but the results, of course, are way better when the system can use word vectors for like a specific language, in this case Tibetan. So again, since the current number of manually corrected tokens for all Tibetan is too small at the moment, I'm dealing with that, but of course it's a very slow process. To train any kind of neural network based model, we resort using classical Tibetan instead. And this is why, again, why we normalized all Tibetan to classical Tibetan. And for classical Tibetan, and to create like the word embeddings, we use the fast text. We, of course, with the aim of improve the results of the tagger, and with word vectors that are based on a large amount of Tibetan data digitized by the BDRC and annotated by Nathan Hill and Maria Lee, and deposited like on GitHub on the annotated corpus of classical Tibetan. So we then, of course, divided the above mentioned large amount of tokens. We are talking about more than 300,000 tokens of classical Tibetan gold standard in training, test, and development sets, 80% and 10% and 10% respectively. And we trained the tagger with these word embeddings, and we evaluate the results with two sets of tags. One is a small universal dependency part-of-speech tag, which is so the tagging that are like proposed by the Universal Dependencies Project, and versus like a larger amount of tags. So these tags like are like noun, adjective, numeral, determinal, adposition, and these are adverb and so on. And these are the tags used by the Universal Dependency Project, but we prefer to use a larger set because it retains some morphosyntactic features that are kind of handy in the case of the parsing of the old Tibetan corpus. Like the genitive, for instance, that introduce relative clauses. I will show you like an example in a little bit. And then we end up with a verb lookup in a verb lexicon. And this is like the part-of-speech tagging test results. And we were very happy. So we already found, to be honest, lately, like a way also to improve word embeddings. So that should make the neural tagger even better. And we can see that the neural network tagger is working better with larger like tag sets, and the memory-based tagger is working better with the smaller tag set. But as we said, we want to use the larger tag set for our purposes, so we will keep using the neural tagger. And also the while-in transliteration, which was in use till like 10-15 years ago, nowadays has been replaced by the Tibetan UTF like Unicode, so the one that I showed you before. So this is the reason why we rely more on the neural network. And to be honest, these were the results on the first run, so they were kind of promising. and we already seen some kind of improvement, as I said, because this is a work in progress. Of course, we expanded now the Old Tibetan corpus, so we kind of manually fix the errors. So there is like an ample, I think, margin of improvement. Then we went to the parsing section. So for the purposes of parsing, as we said, is more beneficial to keep more tags, such the agentive particles and genitive particles, and as I show you now. So we wrote an elaborate rule-based grammar, combining the part-of-speech tags generated by the neural network model into its constituents, and then this gave in automatic way a shallow parse results that are comparable to what is like the what is called the historical Penn tree bank corpora. So the output, so the errors, as I said, has been like corrected to create, of course, gold standard. And the output is converted in various formats, so scholars from various fields, of course, can use any search method they prefer. And this is an example of the results obtained. So this is like a sentence, and this is the parse representation. And it looks, and it came out very, very nice. I would say this is like even more complex, where you have like a relative clause introduced by these particles, which is a genitive. This is why we retain like more a larger tag set. And of course, like there are like the part-of-speech tagging errors that has to be taken into account. And this is why we need, of course, the manual error correction. For instance, when you create word embeddings, the problem if you have like some homophones like case particles and converbs or even nouns, you can use the context to create, to make some kind of disambiguation. The proper nouns represent still a problem because they are sometimes like compound nouns, and they are made of long sequence of syllables. This occurs in many texts, and above all, like in Old Tibetan, which are like historical texts. So you have a lot of like toponyms, name of kings, name of person, and the tagger in this case cannot be, cannot recognize them, of course, but recognize them as, I don't know, like as a verb, like as a noun. So what we are trying to do is just create a list of these toponyms, like of proper nouns, and check them if they don't have any reduplication with like common nouns, because that could create like a problem. And we really are retraining the model once we have like a complete, like a definitive list of this noun, to improve even like these problems. And the final, of course, action will be the one of then normalizing the Old Tibetan and converting back to from classical Tibetan to Old Tibetan, using again the CG3 grammar that I showed you before. And so this is like on the right, this is like a visual representation of the part-of-speech tagging that has been created with our model. And you can see that each word has a tag. You have the case, in this case, the noun, the verb, and again, this has been like a useful like conversion methodology, I think, like for extremely low resource languages. And in some time from now, we are planning to deposit our first Old Tibetan tree bank on GitHub, which is a small but big achievement. I think that can be open and pave the road for further like studies in machine learning NLP applied to low resource languages. I forgot maybe this is something I should have said at the beginning. So the tree bank is important. What is the tree bank? Tree banks are often they're created on top of corpus that has been annotated with part of speech tags, as in our case, and they can be created, of course, manually or in semi-automatically, or like completely like in automated way, like in this, not in this case, but and they can be like their foundation, like for many use, like they can be used like for in computational linguistics. They've been using for part of speech tagger, again for parser, for like semantic analyzer, and machine translation system. So it's just not a theoretical like problem, but it can be then applied to also like some practical like cases. And now we start to talk about the exploration of the classical Tibetan corpus. So as I said, like the project that we are working on is focused on verbs. And we basically try to create, annotate the predicate argument, so the verb, subject, object, like link structure of verbs in this big corpus of Tibetan text. The guidelines that we use are follow. I want to show you this first. The Universal Dependencies Project. And basically, we are linking predicate to not to the function word, the case marker, but to the argument themselves. Let's make this simple. Basically, what is an argument? Like subject and object are two direct arguments of a verb. Like I give, or I read the book, for instance. I, in this case, is arg1, which is the subject. The book is arg2, and read is the verb. If you have like a case marker that is follow one of the arguments, so I go to China is considered like an oblique argument. And then you have other kind of dependencies like oblique arg or auxiliary, but these are the three main argument structure that will appear in our annotation. So this is like, again, the Brat annotation tools, and these little arches basically create the dependencies. They are manually drawn and create like dependencies between the verb and the arguments. So what we want to do, since we have like a huge amount of data, we want to use like a neural network model in order to create in an automated way this sequence labeling, so the labeling of arguments, and basically training the model with the manual annotated like sentences, allow like this model to create an automated annotation of these arguments. Again, we are dealing now with a corpus that is made of maybe kind of million tokens. So of course, it's very, very hard. We won't be able to annotate the whole thing manually. So this is why we are more and more inclined to use like machine learning techniques, and it's working, I would say, pretty well. we were here, sorry. So the classical corpus that we use as golden standard, so that has been manually annotated, is compounded by different texts. There are like the Shanlung, and this is like a brief description of what is this text. Then you have some hagiographies, some bibliographies. They are like, so we tried to include in the original manual annotation to diversify the genre in order not to focus only on one kind like of text, like, I don't know, Buddhist text translated from Sanskrit, that they have a very, very like specific morphosyntactic like structures. And again, the model has been trained so far on classical material, so is working on old Tibetan material, is not working that well because we didn't train it so far with the modern spoken material. No, it's working with old Tibetan, but it's not working properly with modern Tibetan because it needs more training. But of course, that has to be expected. So this is the description of the text that we use, the Buton Chochung, and some of them are very repetitive, so not very useful for training. And again, so we've been trying to sample from very classical text, and in order to, again, to have a huge variety also of their argument structures. And of course, even here, there's been additional steps because the part of speech tags in this case has been generated from the neural network model that I showed you before. So there is also some kind of human intervention in terms that if we want to use this as golden standard, we have to manually correct the part of speech tags where it's needed. And also we have to try to be very consistent with the manual annotation itself. Again, this is an example of manual annotation of a Tibetan text that we will try to then reduplicate with the neural network model. And so the sentences that have been like manually annotated are around like 10,000 for classical Tibetan. Then you have to add around like 3,000 sentences that I annotated for old Tibetan. And this could be a good amount of instances for training a machine learning model. And yeah, this is like a short introduction, maybe not so interesting for you on machine learning, but machine learning applied to a linguistic problem. So so we want to predict this pattern, this pattern, and this model has to learn from patterns of linguistic information. We have two fundamental approaches. We have unsupervised learning, and that is purely based on raw data, and we'll find then common structure and pattern data. And we have the supervised learning that needs training data, as in our case, this is what we use with correct labels, and will predict the correct labels for raw and labeled data. And then we should have also reinforced learning, but that's is something that we are looking into it, but is something that my colleagues in Munich are dealing with. So we are still not there. Yeah, so with the supervised learning approach, we have the data, which, as I said, is made of 10,000 sentences, manual annotated in this Brad tool that I showed you before. And they all have the verb argument structure. And the task, of course, of the model is to classify the new data. So find the new verb argument structure of unlabeled data. And then we have like a performance measure, so the accuracy of this classification. The input of the data is in the conlu format. So briefly, the conlu format is a standard format that is followed to annotate data at sentence level and word token level. So basically, the word lines, they contains the annotation of the word and the token in 10 fields. One is missing here, and every field is separated by a tab. The blank lines mark the sentence boundaries, and each word token here basically has 10 fields that represent different attributes of the token of the word of the token, so the syllable in this of the word, sorry, that are like the ID here, the first one. Then you have the word or token, and then you have the lemma, so the lemmatized form. I don't know, if you have went in English, the lemmatized is to go, so the infinite form of the word. Or if you have like some allomorph that occurs in Tibetan, you kind of normalize them to one form. Then you have like the universal part of speech tag here on this column. Then you have other features here that can provide more specific, like a part of speech tag or morphological features. And then you have, which is important, like the head of the current word. So what means the head? So in this case, we have an argument, oblique argument. At the end, it's number 6 here. The verb. So this is and again, this is R2 is an object of this verb. So his head is like the verb here. And then you have the label here. One is an oblique argument and one is R2. So we want to train with this like sequence of label, the neural network model, and see how good it's going to be to predict like and label data. So the training data, again, like is a sequence of word with part of speech tags. And we have like corresponding sequences of labels for each word. And we want, again, we want to predict the correct label sequence for new sequences of word. And the neural network model that consists, as probably you know, different layers where the output from one layer is the input of the next layer. But the first layer is the most important because it's the vector representation of word with the corresponding context. We call it like the semantic dimension. And the last layer will be the classification, so the probabilistic predication of my sequence. So this is a kind of visualization of what is happening inside the model. And the central, again, like the central element is a recursive neural network, and actually is a refined recursive neural network that is an LSTM that is way better for long sequences of words. And we use like an LSTM because, I mean, as like feedback connection, and it's way better for like handwriting recognition, speech recognition, like labeling. So the is a standard like for sequence labeling tasks. So this is like an example. So how it works, again, to visualize how it's working the model. So it's like Nge Kerang La Deb Marpo Chin. I give you a red book. So here you have the subject, Ne, the oblique Kerang to you, Deb is the object, and this is the verb. Again, a visual like representation of what is happening with the word embeddings, and we split the training, like the sentences, like in 80%, like 8,000 sentences, use like the training data, 1,000 sentences like a development data, and 1,000 like a test data, and we receive like an accuracy of 88%, which is not bad. Here is like the model accuracy like graph, with the number of epochs, and considering that the model can be like hugely improved again, like with like refined again, as we said, with a larger corpus, including all Tibetan, modern Tibetan material, and so creating like even better like word embeddings, also like golden data to retrain it. It's really again very promising, and we are currently we are using for the classical Tibetan. Even if when we create at the end the lexicon, we will flag these sentences as created, by like a machine and not human checked, because we won't have time to check, I don't know, 100,000 sentences if they are correct. But we were sampling some of them, and results, at least if the sentence structure is very like simple and linear, there are no problems. But if you have nested clauses, sometimes can be an issue. And again, like as future work, we would like to combine again like the LSTM model with also the rule-based model that we created at the beginning, and I will show you now briefly like an example. And so this is, for example, like a combination of the two approaches. So we have the arguments here, the oblique, the oblique here, the R2 that has been produced by the neural network model. And then we fill the gaps. What does it mean? That we created the dependencies between the remaining part of speech tags using a rule-based grammar, the CG3 grammar. And this is in order to create like a full dependency corpus of Tibetan that still doesn't exist. And this is not a spin-off project of our actual project. So, and this like you can see, I think is nicely fit of how the two approaches can like live and cohabitate like together. I'm going to end this presentation with saying that there are still like problem to address. Above all, we don't want to propagate error of part of speech tagger to the annotation of verbs, and that's an issue, because as I said before, the tagger works well with certain text, but with other texts where, for instance, again, like the old Tibetan text where you have a lot of proper nouns, we need to be careful and like correct all possible mistakes, because the foundation of having like a very functional and efficient like neural model is to have like the training data as accurate as possible. So, and that requires a lot of like man work. And I'm going to add that this could lead also to the creation, for instance, in the future, of a noun entity recognition tool for Tibetan that doesn't exist at the moment, or at least it doesn't exist, like I think, outside of China. And so, yeah, as you can see, like this has been a research, like a purely like theoretical problem, but that could lead also to the creation of some NLP tools that could be used by the Tibetan speaking community in developing like tools for their language, can be used for, again, like machine translation, alignment of bilingual text, and so on. But yeah, I mean, the road to go is still long, but I think that the results that we obtain have been quite promising. So thank you.
Okay, thank you very much. I'm like clapping to you. I hope people at home is still happy with the talk. Very interesting. I have a couple of questions, but I see also that we have a question from the student. Before reading
Okay.
it, I encourage you to make other questions if you have them. So the first question is from Giovanni Battilana, who says, "How do you know how many layers and elements you need in the neural network model to predict words?" That's a huge question, I know, but
Yeah,
please
it's a
give
very
us your
big
point of view.
question. Uh, how many layers do well, I mean, we did model, so we didn't address this issue so far. So so to be honest, it worked. We kind of uh, sorry.
No, maybe there was a noise because.
Okay, yeah. Okay. Um, so, well, it's a it's a huge question. So at the moment, we are just exploring these tools, and we didn't create them like from from the ground. So I don't think I can answer properly, like from a technical point of view, to this question. So
Okay,
uh,
maybe I make comment.
yeah,
I can comment this question. I mean, it's a totally irrelevant question, but as I probably and now I'm talking to the students, as I probably told you during the previous lectures, when you build a machine learning system, there are several components. The actual machine learning technique is just one component. Usually, it's not even the most important component. Of course, the overall, let's say, effectiveness of the system you're building. So in this case, maybe the system is to annotate. It's a system for annotating these resources language. When you build such a system, of course, the accuracy of the machine learning component is important, but maybe is not the most important one. That said, what usually people do is to take an existing solution that has been shown to be, let's say, accurate, effective enough, and decide consciously not to mess with the parameters of that solution. Okay, because there are many other parameters on which maybe the person, the designer of the system is more expert on. Okay, so possibly maybe Christian, this is also your case. You
yeah.
said this is a neural
Yeah.
network that I have. I trust that it has been let's say tuned, and in the hyperparameters it has been tuned in such a way that this is good enough, and I still have many other things to be designed and many other parameters to be chosen, so I don't mess with the neural network basically, right?
Yeah, we modify something, but of course the core code hasn't been touched. What we use basically is just off the shelf tools, and at a certain extent we kind of tweak them, but we, again, as you said, if they're good enough for our tasks, we just use them. So, and sometimes for a language like Tibetan, some model is better than the others. And I saw that, for instance, I'm working with Uyghur now, and I'm using this framework called NLP Cube that is developed by Adobe, and is good enough for Uyghur. So we, of course, I mean, we train the model, we know how it works, but we don't mess with it, with the core structure. Of course, because it's not our primary tasks. Of course, it would be nice to go and see how it works, but we have a research to we have to have an outcome. So I mean that's for us and for many other people working like in NLP. Probably this is like the sometimes the approach. So
Okay, okay. Another from a broader point of view to the student again. the problem of deciding which is the best architecture of a neural network for a given task is, let's say, an open problem, is a very hot topic in research. Well, a way of looking to this problem is as an optimization problem. Basically, you are searching in the large is diminishing term in this case, in the huge space of architectures of neural networks for the one that maximizes some metric in which is basically the effectiveness in a task or in a set of tasks. So it's a very large problem because one of the let's say features of this problem is that it is true that training a neural network, in particular those who are large, is a heavy task from the computational point of view, and so it is particularly, let's say, more true that training a model for optimizing the architecture of a neural network is even heavier. So that's a not topic in research, something that is not often, but sometimes taken with evolutionary computation, which is the last topic that we will see in this course. Okay, we have other two questions. No, well, one is a question and the other one is a thank you from the student Giovanni Battilana who posed the question. The other question is from Babai Elam. You define some other data sets other than training and test?
Sorry?
So the question is, did you use some other data sets other than training and test? So maybe the student is referring to a validation test, a validation data set or something like that. Not fully clear to me the question, but if you may extract some.
Yeah, we didn't. I mean, those are the data set that we use. Yes, I'm not sure if it has been clear enough or yeah that.
Okay, maybe Babai Elam, can you clarify?
In the meanwhile, may I ask you another question?
Okay.
Yeah.
Can you just tell your name because otherwise we don't know where to look.
Semi.
Okay.
Thank you for the presentation.
You're welcome. Thank
you. I would like to know if you tried any other model before to finalize this one, and how long time you spent to reach the final results?
You mean for the tagger or because with the memory, with the part of speech tagging, we did use this statistical supervised learning approach, this memory-based tagger. And as I showed you before, that the results were good, but we kind of found that the neural tagger with improved embeddings it was kind of good enough or even better. If you use other neural network model beside the one that I introduced, again, we just used that because it was working good enough for our purposes. So we didn't compare different neural network models and the accuracy and the results. And how long in terms of training, you mean, or?
Yes, in terms of training.
It took some time, yeah. To get the results, for the tagging problem that has been done on the computer of my colleague. I think it took a couple of, you mean in terms of time, couple of days. And for the other problem, like the sequence labeling, the training has been done by my colleagues in Munich. So I'm not sure how long it took some time. It was not, it was not extremely time consuming, but it took some time. I don't remember now. I mean, how long it has been. But even that, I mean, that is something that we found that it was working, and again, we kept using it. It doesn't mean that we won't use in the future other models, but again, since our task was to kind of we use the tool to achieve the results, and the results already was good enough, so we kept using this model that for other like colleagues were using, and they said, okay, this is good, try tweak it for Tibetan. So we haven't started to do like a proper comparison beside the memory-based tagger, like with other like neural network models. I don't know if that's answer.
Yes. And another last things is,
Yep.
Could this method export to other languages?
Oh yeah, definitely. I mean, definitely could work with other languages. Actually, I would like to use both the memory-based tagger and the neural network tagger for Arabic script, and which is like the script used for Uyghur language that I'm working on now. I'm creating like a corpus of, again, like an historical corpus of Uyghur. And yeah, definitely. The whole pipeline also for another resource language, for instance, when you have like a very low resource language like Old Tibetan, the idea of normalizing first to the classical form and then proceeding from there also is like something that can be adapted to many, I don't know, historical like text, I don't know, like 17th century Arabic script. I don't know, just making like an example, but of course it can be exported like the whole thing like to other like languages to investigate.
Okay, thank you. I'm happy because I'm seeing that questions are coming in the chat. So there is a clarification. We have more or less half an hour, so I don't think we need to be in a hurry for the questions. We have the clarification from Babae Lama, who writes, I think I saw something like development data in the slides. So the question is, what's that development data? It's a different, let's say, usage of the data like you do with test and training.
Well, it's the usual like split like in the three data set that you use to train, validate, and then tune the model. I mean, just
okay. I think the answer is clear. I hope it is clear to the student too. Then we have another quite specific question from Gabriel Sarti, a student who worked and who is still working on NLP quite deeply. He is asking, thank you for the talk. Did you experience some problems with the by LSTM, CNN, CRF tagging performances over long range dependencies? So are long range dependencies a problem for this technique, according to your experience?
Not so far. I mean, just if you're asking if the dependency of word like the fact is that we try to, I don't know if this is the right answer or what you're asking, but I mean, we try to use a sentence boundary, these punctuation markers like this share, so we didn't create dependencies across sentences.
Okay.
So yeah, so we didn't cross border sentences, so we didn't create like really we didn't retrieve dependencies of verb across this kind of share, this utterance that we created. So not so far. I know it's not the most correct thing to do, but we had to start somewhere to create the sentence boundaries, and that was the easiest. We are now working on to improve like the kind of sentence boundary definition in Tibetan, which is not very easy. But no, we didn't encounter so far any problem. Yep.
Maybe it's also a matter of the kind of text that you are using. Maybe it's, I mean, the very content itself is not does not require long range dependencies. I don't know. Maybe since it's historical text, maybe not so complex in the story. I mean, or not.
No, well, it's not. It's not that complicated. Yeah, no, but yeah, you don't have like uber like complicate like dependencies sometimes, because you can have like nested clauses in the language, so that is also a problem within the problem. So yeah, but I mean, usually it's not like this long. It's as you said, it's not that complicated.
Okay, thank you. So we have another question from Morichetti Pietro, who starts by thanking you for the presentation. Then he says, it's moved. Did you consider some kind of parallel text mining programming for large text processing? So this is, I think, more about the implementation rather than the algorithmic part of your talk, right?
We didn't consider, if you mean like parallel text, but we didn't consider that so far. I mean,
probably because you took the implementation for the tool that you used as it was. Without messing on the code, because
you have other
goals.
I mean, there are like all possible things that we could do, but again, I mean, it's more like a kind of reverse engineering approach for us. Just we use the code and we look at the code, and if we have time and it's not working, maybe we look to a different tool. We try to tweak it, but so far we didn't look at this approach. No.
Okay. Now we have another question, which is on let's say another level of abstraction. Ruggeri Gabriele, I suppose, who asks, could this technique and approach be used, let's say, to predict how a language is going to evolve? So, for example, to see how it will be or look like in the future. Interesting question. I mean, not just this technique, but these kind of techniques in general. Can you, since you are probably the most expert person here to talk about languages, can you predict how a language is going to evolve using text mining?
Well, I mean, since we are dealing with the diachronic text, so with historical text, you can see like the variation, like in spanning, I don't know, like 1,500 years. So you can see like the morphological like structure changing. You can, if you are like clever enough to diversify the text that you're training the model, theoretically, I mean, that's interesting. I mean, because we never thought. We usually explore the variation happen in the past. Because we want to have like an historical overview of how the language evolved in the past. But maybe you can make like a prediction of.
In principle, this could be a new research topic: predict where the language will go.
However, well, definitely. I mean, and the more material, of course, that we have. For instance, now we don't have so much modern Tibetan material. I mean, we do have it, but we have to tweak the model and train it again with including the modern material, and that, for sure, we could give some indication. I mean, that's interesting. We always will look at the past, but it would be interesting, like to have like a prediction, not only for Tibetan, I think for every language.
I have the feeling that possibly the times the time scale which is involved in the phenomenon of language evolution is probably too long to be of interest of the current research in machine learning. However, it's a nice perspective. We have another question from Marzio Kevin, or Kevin Marzio, I suppose. Did you use other indexes beside the accuracy to compare the neural and memory models? So it's about model comparison, basically.
You mean about the data, like the accuracy? Well, we haven't. No, we just use the accuracy and we calculate the F score and all this at the beginning, but we've done just like a test on the accuracy. Yeah, with.
Okay, thank you. Okay, so while we wait for other questions from students, I do my questions. So the first one is, we say that this language, like other languages, are low resources. But is this the only motivation for which, let's say, research and tools for natural language processing are, let's say, behind with respect to most common languages, the fact that we have less documents basically, or it's also related to the structure of the language itself? I'm thinking about the fact that the syllables are not separated, that the sentences are not separated, that you can tell where a word is starting and stopping and so on. So just a matter of few documents, or also the structure of the language is, let's say, bad from the point of view of text mining?
Well, I think it's both. I mean, well, for Tibetan, let's say all Tibetan, if you can split the two things, as I said, is really low resource language, and it differs, but it's also like, it's an old variation of Tibetan. So I think that not only for Tibetan, but the problem is just to have like available data. And with Tibetan, we are getting there because a lot of, for instance, like a religious text from these like Buddhist centers has been digitized. And so it's easy to retrieve them, OCR them, and have them available. So on the other hand, the fact that the structure of the language itself, like you say, like there are like no clear like word boundaries, like sentence boundaries, is a new challenge. So the existing tools or the off-the-shelf tools has to be, as we did somehow, modified. So I think it's a combination of the two. And so is on one hand the lack of, for instance, I'm looking into Uyghur now. And Uyghur does have material, but not enough material like corpora to work on. So, for instance, way behind than Tibetan. Mm-hmm. And this is why we try to create a corpus for Uyghur. On the other hand, maybe the tools used for other Arabic, like agglutinative languages as Uyghur, like Turkish, mm-hmm. Come into the picture. It can be used, while Tibetan, since it's really peculiar, you don't have other comparable language, then of course it's a problem of creating from zero or readapting already existing material. So I think it's twofold problem.
Mm-hmm. Okay, thank you. Well, I have another question, more practical.
Yeah.
Maybe you said it and I lost it, but since you also work with historical documents, where and how do you do, or someone for you does OCR for transforming the image in digital version of the document?
Mm-hmm. Well,
Sorry,
historical.
OCR. I don't know if everyone knows. OCR is optical character recognition. Is basically a computer vision technique for transforming, quite old. Okay, for transforming the image, the digital image of a piece of paper with some text in a text, the digital version of the text itself. Okay. Sorry, you can go on.
Yeah, well, again, we are lucky enough that most of this text, or at least the one that I'm working, being already, for instance, the old Tibetan documents that are here at the beginning is this one here. These are like. These have been like all photographed and preserved at the British Library and at the Bibliothèque Nationale in Paris. And furthermore, they've been all of them, like in decade, have been already transliterated, this Wiley system. So
manually or automatically?
No, manually.
Okay. So no OCR basically.
No CR for these ones, all
Okay.
Tibetan, but for modern texts, we are actually using transcribers. I don't know if you know the transcribers is very handy, and you can create is a online tool. And you can create within. We are using that for Uyghur now. You can create your model within like the online tool, so tweak the parameters, training, and it's super efficient to, for instance, recognize handwritten like Arabic. We were testing like that now, and it's really promising. So, but in my case, like I had only to create the Unicode, so from the transliteration to create the Unicode Tibetan. And with some like Python codes, because I mean the conversion tools available online, they were not enough kind of accurate. And but yeah, from a practical point of view, again, we are lucky enough that we have the resources. Maybe they are not ready. We have to pre-process them, but at least for Tibetan, they are there. Yes, it's not that we have to go in Central Asia and scan some obscure like manuscript in a monastery and chased by, I don't know, the Chinese Secret Service. No, it's not. So
okay, thank you. Just to give some context to the students, the OCR problem is one of, let's say, most ancient problems in computer science, because from when we have computers, people, basically countries, started to try to use computer to process paper documents, which is of course a good idea. So scientists were trying to solve the problem of OCR even before we were talking about machine learning, computer vision, and so on. Still, a very common OCR problem is one of the most common used tasks for assessing novel and not novel or variation of existing techniques in computer vision, which is the so-called MNIST problem, in which basically the dataset is composed by a collection of manually handwritten digits acquired as images that has to be classified as the corresponding digits. So a multi-class problem with basically 10 classes. But however, we can say basically that the OCR problem is solved, even in particular when we use OCR for as a component of a more complex system. Okay, I have. If Christian, do you have some other time, some other minutes for another question?
Oh yeah.
Okay, perfect. So I have another question about the annotation.
Yeah.
How often in this task that you told us about, but also in the
You're
other
talking about
task?
manual annotation.
Yeah, annotation. Yeah, in general, how often did you experience the fact that you find that you found that the, let's say, the outcome of the machine, the system, was correct and the annotation was wrong. So for example, you have this annotation saying that, I don't know, this is argument 2, but you think by reading the text and also because there is some interpretability in the text that that's not an argument 2, it's an argument 1 or something like that. Does it happen often?
Well, it does happen in terms that the machine, of course, is more consistent, and and that is helpful. So when you manually annotate, I think that sometimes you have some degree of you can read the context, and maybe the problem is maybe if you have two annotators, even if you have a guideline that we try to write down universal dependencies like guideline to be and discuss before starting any annotation of new pattern discussed between the team, still we noted a degree of interpretation, like what is a head noun of a nominal phrase. If you have an opposition between two nouns, I mean, I don't know, for instance, to keep the leftmost element of my nominal, like, I don't know if there is, here it just is an example. Okay, here is like lompo cheek. This is like a nominal phrase is a noun and a determiner here. So here it's easy. The leftmost element is the argument. Lompo means chief, and then you have like the one chief. I don't know what they are talking about, but anyway. But sometimes if you have like two noun in that position, where is the focus? So annotator sometimes, machine can be more like, of course, is consistent, and that is big plus. And sometimes, but not that often, but sometimes we found that maybe we overlooked things, and maybe that the way that the machine solved the problem was in a way acceptable, maybe more consistent with the annotations. Yes. So yeah, we found this kind of, but I mean, again, it's interesting because I mean it's hard to be consistent even if you're manually annotating for yourself. So.
Okay, thank you. I have a final question. I often tell to the students that in order to build an effective design and build an effective machine learning system, you need to have some domain knowledge, so some knowledge about the problem that you're trying to solve. Or if you don't have it, you need to work together with a person having it. So let's say, my question is, do you think that a person would be able to do this kind of research and enjoy it, possibly, not knowing anything about this language? So, like me, for example, I don't understand anything about what's written on this slide, of course, but so do you think that I would be able to do something here in tagging, understanding, and so on without knowing what's written?
I mean, of course, knowing the language is helpful, but for instance, again, I'm talking about Uyghur. I don't know Uyghur. I know a bit of Kazakh, I know a bit of Turkish, but Uyghur and even the script, I didn't know the script, Arabic script. So for me, it's like, looking at this, like you looking at this thing, and of course now I got a bit of training. So, but yes, definitely. I mean, just depends what you're using that for. But I mean, definitely you can approach the problem once you have like an idea of how a language works. I mean, you don't have to have such a deep, I think, knowledge. Of course, then you have an expert. You can ask advice. Depends also which is like the task. If it's to write, to build, I don't know, a part of speech tagger, like a searchable corpus, I don't think that it requires to be like the expert can be done. Actually, maybe it's even sometimes better. I don't know, because it frees your mind from other approaches. I don't know, but that's just my interpretation. But yeah, definitely, of course.
Okay.
Yeah, of course, like a basic knowledge of reading, of recognizing things, but again, you don't have to be like like I don't know, like a linguist in Tibetan Burman languages to work on Tibetan. It can be a mix of things. Again, it depends on the task while you're building these things. If someone is just working on their source languages and want to write like a parser, part of speech tagger. My colleague, for instance, Marieke, she works on Welsh language. She's working in Cambridge, and she started to work on Tibetan without knowing Tibetan. She liked the language, some morphosyntactic features. So yeah, why not? So
okay, so there is some hope. You can, if you want to work on Tibetan, you can do it even with. You can start.
Yeah. We are happy to have people, of course, more skilled than us, just on like the computational, like and coding side. Yeah. So yeah, just team up.
Okay. So thank you very much. Thank you for accepting the
Welcome.
invitation, and thank you for the super interesting talk. I think
Thanks
there
for
are.
your time in listening. I hope that it hasn't been too like boring.
No, super interesting. I think there are no other questions from students, so we can stop the lecture. Christian, if maybe we can hang up in a couple of minutes on Meet, so I
Okay,
can thank
sure.
you. Okay, and so
Okay.
thank you to the students and the other.
Thanks
coming.
everybody. Thanks.
And see you. For the students, we have a lecture tomorrow in the room, okay, with the lab activity. Okay, I'm stopping the recording. Bye bye.
Thank you. Bye.
Thank you very much. Goodbye.